Okay, so a couple of things we want to go over before we actually get into the dosage calculation, and that's our units of measurement in our measuring system, just to review to make sure we're on the same page. And we're going to start off with the metric system. And the metric system, it's all about the prefixes. Each type of measurement in the metric system only has one unit. For mass, that unit is a gram. The gram was actually defined to be the mass of 1 milliliter or 1 cubic centimeter of water. For capacity, that unit is the liter. Of course, now for our purposes, the liter is actually quite large, so we tend to use the smaller units, which involve the prefixes to make them smaller. And we'll go over those prefixes in a little bit. For length, that unit is the meter. Now, if this were a full course and we had more time, I'd go over the difference between mass and weight. The metric system tends to focus on mass, which is a more precise measurement. It's the amount of material in an object, or if you're looking at the mass of a person, it's literally the amount of particles in their body, where weight depends on the force of gravity. In our standard system, we tend to focus on weight. When we convert between metric and standard, we're a little sloppy. We convert standard weight into metric mass, but it works out okay because on Earth, gravity is relatively constant. Anyway, let's get to our prefixes here. So from those basic units, a gram, a liter, or a meter. Now I'm going to date myself a little bit, but you always see me write a capital L for liter, because that's what I was taught, is you had to use a capital L for that. It wasn't until just a few years ago I would learn that wasn't true. The reason I was taught that you used a capital L for liter was because back in the day when I was young, before we had all these fancy computer type fonts, your typical type font, the number 1 and the small l were indistinguishable. So if we had something like that, trying to tell if that was 51 or 5 liters was tricky. But if we had a capital L, we knew there was 5 liters. So your books usually will use a small L now because of those type fonts. If you see me using a capital L, that's just force of habit. It really doesn't mean anything. But that's our main unit. And we can think of that main unit as being 1 unit. Or we typically think of it as 10 to the power of 0, which is equal to 1. If we need to measure something smaller, the metric system uses prefixes for that. And going smaller from our main unit, the first prefix is deci. So we would have a decigram, abbreviated DG, a deciliter, abbreviated DL, or a decimeter, abbreviated DM, which was 1/10 of the main unit. So that deci prefix means 1/10 of. So a decigram is 1/10 of a gram. Keep going smaller, we had centi. Centi was 1/100th. So a centigram was 100th of a gram, or a centiliter, 100th of a liter, centimeter, 100th of a meter. Then we had milli. Milli was 1,000th. So the same thing, a milligram is 1,000th of a gram, milliliter is 1,000th of a liter, millimeter is 1,000th of a meter. For liters and grams especially, we tend to only use the main units and then the millis. We do see deciliters used quite a bit in the medical fields for our lab testing. Blood glucose is milligrams of glucose per deciliter of blood. Most of your urine testing is the same way. It's per deciliter of fluid. That's about the only place where I've seen that prefix of deci used consistently. Otherwise, it's mostly the milli. Now, if we keep going smaller, we skip over. We don't go every 10. We skip over the 10,000th and the 100,000th. They don't have units for those, or they don't have special prefixes for those. And we skip down to micro. Micro is a millionth. So the official abbreviation for micro, I'm going to scroll up here so I got a little more room, is the Greek letter mu. So microliter would be mu-L, microgram would be mu-G. The medical field is one of the first fields that had to keyboard everything into a computer, and there is no key on the computer for the Greek letter mu. So from what I've seen, and Karen can correct me if you guys do it differently now, is the medical field tends to abbreviate it MCG for microgram and MCL for microliter, so that they don't have to search for that mu key. Perfect. Going larger then, we had deca. Deca means 10. So since DG was deci, we use DAG or sometimes use DKG for decagram, DAL for decaliter, and DAM for decameter. So that would be 10 grams or 10 liters or 10 meters. I've never seen that unit used in any sort of practical application. Hecto is the next prefix, which is 100, sorry. And so a hectogram was 100 grams, hectoliter is 100 liters, hectometer is 100 meters. Outside of land surveying, I've never seen that prefix used for anything practical. So the next one that gets used consistently is kilo. A kilogram, since a gram is so small, the kilogram is what we typically use for our standard unit of mass because it's more closely related to the pound. Kiloliter is actually quite large. A kiloliter is about 270 gallons, so we don't use that one so much. Kilometer for distance gets used quite a bit, and that abbreviation kilo is 1,000. Well, just like going the other direction, we skip over the 10,000th and the 100,000th. On the upper side, we skip over the 10,000 and 100,000 and go up to 1 million, which is mega. I don't see you guys having to use a lot of the abbreviation mega, but for some very large dose medications, you might run into it. Since we use the small m for milli, we use a capital N for mega. So capital MG would be a megagram. Capital ML would be a megaliter. So 1 million grams or 1 million liters. Notice I didn't even put it up there for meters because 1 million meters is like 40 times around the equator of the Earth. So it's not a very practical unit. Our conversions here then are based off of these equivalencies. Now, there are a lot of textbooks that will show you, and if this is the way you were taught, this is actually how I do it because it's quicker and simpler to just move decimal points. If we have 0.038 milligrams, and I need to convert that to grams, I use the chart. Here's milligrams, and I'm going to regular grams. And if I just move from milligrams to grams, it's 1, 2, 3 spaces on the chart to make that move. My decimal point has to also move 3 spaces. Now on the chart, it was 3 spaces to the left. My decimal point has to go 3 spaces to the left. So I go 1, 2, 3. That becomes 0.000038 grams. If I have 0.6 milliliters and I want to go to microliters, similar type of thing. Looking on the chart here, here's milliliters. Microliters is over here. That would have to move 1, 2, 3 spots to the right. My decimal point would move 1, 2, 3 spots to the right. I go 1, then I have to add zeros, 2, 3 to get 600 microliters. If you can remember all that, that is fine. Like I said, that's how I do my metric conversions. But I understand that requires you to memorize this chart, and not everybody has that done. So we can use a process called dimensional analysis, which is our typical measurement conversion. So if I want to go from 0.6 milliliters to microliters, what I can do is set it up like this. My 0.6 milliliters, I turn it into a fraction by putting it over 1. Now you might be thinking nothing gets better when you turn it into fractions, but measurement conversions is the one time where fractions are very useful. We're getting rid of milliliters, so I have to put milliliters on bottom here, and we are converting to microliters. If you think of our rules of fractions where you cross cancel, the milliliters are now going to cancel out, and we're going to leave our units of microliters there. The numbers that go in are the numbers that come off the chart, so we do have to at least remember those. A milliliter is 1,000th of a liter. A microliter was 1,000,000th of a liter. And then we make sure you get enough zeros in there. We do that calculation. So what this is saying is we're going to take the 0.6 times 1/1,000,000th. So on the calculator, we would do that as, if my calculator comes up, there we go, 0.6 times, I'm just going to put 1 divided by 1,000,000 in parentheses. And then I have to divide by the 1/1000th. So I'm going to divide by, and then in parentheses, 1 divided by 1,000. And I get, now, oops, what went wrong there? I put the wrong numbers in. Sorry about that. I forgot in the metric system you have to switch the numbers for that. You can see I don't use this very often for my metric conversions. Let me try that again. What I want to put in here for numbers is my 1 liter. Got me flustered there by screwing up a calculation. Sorry about that. 1 liter is 1,000 milliliters. 1 liter is also 1,000,000 microliters. So I don't have to have the fractions. I put in just the 1,000,000 for the microliters and the 1,000 for the milliliters, and I do my conversion. So I don't need the fractions. It's just the 0.6 times 1,000,000 and then divided by the 1,000. Gives me the 600. So I regret screwing that one up on the dimensional analysis, because dimensional analysis is an incredible tool for everything else. The metric system is the one spot where dimensional analysis is confusing, because you do have to kind of think backwards like that. Are you guys good with doing conversions in the metric system, moving the decimal point? Okay.
Yeah.
I'm going to leave it at that, because the dimensional analysis, like I said, in the metric system is a little bit confusing. Everywhere else, it is a wonderful tool, but that's the one spot where it just really kind of struggles a bit. So now in the standard system, I'm not going to go over the units of the standard system. What I'm going to look at is the units between standard and metric. So if we look at units of mass or weight, I had mentioned earlier, in the standard system, we tend to focus on weight, which of course is pounds. And in this metric system, we focus on mass, which is our grams or kilograms. Our equivalency there is 1 kilogram is equal to 2.2 pounds. Now this is a little bit sloppy. It's really 2.208 pounds, but it's close enough for anything we're going to need to do. So if I have a patient that comes in and weighs 180 pounds, and we need to convert them into kilograms for our dosage calculations, I'm just going to put their weight, the 180 pounds, over 1. And then my conversion factor, my dimensional analysis, I'm going to put pounds on bottom, and I do that so that they can cross-cancel out with my fraction multiplication. And I'm going to put my kilograms on top. And my equivalency is 1 kilogram equals 2.2 pounds. So the pounds have canceled out. Now it's just a matter of multiplying and reducing. 180 times 1 kilogram is 180 kilograms. 1 times 2.2 is 2.2. And then we just have to divide that and reduce it. 180 divided by 2.2 is, oops, my calculator work, 81.82 kilograms. Or if we have to go in the other direction, if we have a patient who gives us a weight as 65 kilograms and we need to turn them into pounds, well, we'll put them over 1, and then our conversion factor is just going to go the other way. We're getting rid of kilograms, so I'm going to put kilograms on bottom to cancel them out, and pounds on top. 1 kilogram is 2.2 pounds again. The kilograms cancel out. I have 65 times 2.2, giving us 143 pounds. And on bottom, it's just 1 times 1 is 1, so our result is the 143 pounds. We might look at converting length. So for length, the standard unit we typically use is an inch. The metric unit that is typically used is either a meter or a centimeter. Well, an inch is equal to 2.54 centimeters. That is actually a very exact conversion. For the stuff you guys are doing, however, it's extra decimal places that we don't need to work with. So what gets used is 1 inch equals 2.5 centimeters. Mainly because if you're doing a quick calculation by hand, that's a much easier conversion to do in a quick calculation. Otherwise, to use the 2.54, you really have to use the calculator to make that work. So let's say somebody comes in, you're taking a measurement, and you get that their measurement is 17 inches, and we need to convert that into centimeters. Well, again, we make it a fraction by putting it over 1. And we'll multiply by our conversion factor. The conversion factor, we're getting rid of inches. Inches are on top, so we put them on bottom. And we're going to centimeters. And 1 inch is 2.5 centimeters. So here the inches cancel out. We have 17 times 2.5 gives us 42.5 centimeters. On bottom is just 1 times 1, so that result is 42.5 centimeters. Going the other direction, if we had something that came in, let's say someone reports their height is 180 centimeters, and we need to convert that into inches. We put the centimeters over 1. In our conversion factor, now we're getting rid of centimeters, so centimeters will go on bottom, inches on top. 1 inch is 2.5 centimeters. We'll cancel out the centimeters. On top, 180 times 1 inch is 180 inches. On bottom, 1 times 2.5 is 2.5, and then we have to divide that out. 180 divided by 2.5 is 72 inches. So 180 centimeters is actually exactly 6 feet tall. There are other conversions that come into play. One of them for capacity is that 1 teaspoon is approximately 5 milliliters. So the same thing. If we have a dosage that calls for 2.5 teaspoons, most of us don't even have, in the medical situation, don't have a syringe that measures teaspoons. You might have one in your cupboard at home, but not here. So we're going to convert that into milliliters. So teaspoons would go on bottom, so they cancel out. Milliliters on top. 1 teaspoon is 5 milliliters. The teaspoons cancel. 2.5 times 5 milliliters is 12.5 milliliters. And on bottom, 1 times 1 is 1, so that is just 12.5 milliliters. Or we might have a conversion of fluid ounces. 1 fluid ounce is equivalent to about, it's actually like 29.6, but we usually just go with 30 milliliters. And so again, let's say we have something that calls for 0.8 fluid ounces. We'll put that over 1 to convert it to milliliters. Fluid ounces on bottom, so they cancel out. Milliliters on top. 1 fluid ounce equals 30 milliliters. And the fluid ounces cancel. 0.8 times 30 milliliters is 24 milliliters. 1 times 1 is 1. So 24 milliliters over 1 is just 24 milliliters. The one conversion that's always frustrated me is grains. Because, like with the centimeters, we rounded it from 2.54 centimeters equals an inch to just 2.5. Grains has been rounded a lot to make the transition. Grains was typically a standard unit, but it has been kind of adopted into the metric system for medical usage because it was such a, pardon the pun, but an ingrained unit in medical dosages that it had to be adopted into the metric system. And when they adopted it, they came up with the equivalencies that 1 grain, now in the standard system, 1 grain, it's 7,000 grains equals a pound. In the metric system, 1 grain, we tend to call it 60 milligrams. It's actually, if you did the calculation, the direct measurement, it's actually 64.8. It's closer to 65 milligrams. I don't know why we don't use 65, but we tend to stick with that 60. So if we have something that comes up as 3 grains, and I need to convert that into milligrams, put it over 1. Grains are on bottom, milligrams on top. 1 grain is 60 milligrams. Grains cancel out. 3 times 60 milligrams is 180 milligrams. 1 times 1 is 1. So 180 milligrams over 1 is just 180 milligrams. We can have the grains going into grams. 1 gram is approximately 15 grains. Now this one's a little closer. It's actually 15.4, but we round it to 15 to make it work. So we might have 0.2 grams and have to convert it to grains. And I do this example partly as a warning. If you look at those abbreviations, 1 gram abbreviated with just G, grains GR. One of the more common mistakes I used to see on the dosage calculation exam and the Math for Health Professionals was students would see GR and think, oh, that's just grams. It's not. That's grains. So you have to be very careful with those abbreviations. So we're getting rid of grams. We'll put it on bottom. Grains on top. 1 gram is 15 grains. Cancel out the grams. 0.2 times 15 is 3 grains. 1 times 1 is 1. So again, that comes out to 3 grains. The one conversion that we cannot use dimensional analysis on is temperature. And I can't spell today. There we go. So for temperature, we tend to go off of 2 basic benchmarks, where water freezes or thaws, and where water boils or condenses. And in the Fahrenheit system, which I'm not even going to try to spell Fahrenheit, I'm just going to put degrees F here. Water freezes at 32 degrees. It boils at 212 degrees Fahrenheit. In our Celsius system, water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. Notice again that power of 10, 100 units from freezing to boiling to make everything a little bit simpler, sticking with the metric kind of theme there. The reason we cannot use dimensional analysis here is there is no common 0 point. In all of our other measurements, 0 meters equals 0 inches, or 0 grams is equivalent to 0 pounds, or 0 gallons is equivalent to 0 liters. 0 is 0, except in our temperature scales. 0 degrees Celsius is 32 degrees Fahrenheit. So since there is not a common 0 point, we cannot use dimensional analysis to make those conversions. So we have to use formulas. To go from degrees Fahrenheit to degrees Celsius. Our Celsius temperature is found by taking the Fahrenheit temperature, and the first thing we do is we correct for that difference in 0 points. So we subtract 32 degrees from it. And then we take into account the difference in the range from freezing to boiling. It's 100 degrees in the Celsius scale. It's 180 degrees in the Fahrenheit scale. That ratio, if I did 180 over 100, reduces to a 9:5 ratio. So the ratio, depending on which one you put on top, is 9:5, or it could be 5:9. Going in the direction from Fahrenheit to Celsius, it's the 5:9 that gets used. So we multiply by the fraction of 5/9. So if I want to convert, let's just take human body temperature, 98.6 degrees Fahrenheit, and convert that into degrees Celsius using this formula. Well, we put the 98.6 is going to go in for F. And now it's just a matter of order of operations. We have to do what's in the parentheses first. 98.6 minus 32 is 66.6. And then we'll multiply it by 5/9. That's just going to be basically, if you have the fraction calculator, you can enter it, or you can just do 5 divided by 9 to enter 5/9. Multiplied by 66.6 gives us 37 degrees. So that Celsius temperature is just 37 degrees Celsius. If I want to go the other direction, if I want to go from degrees Celsius to degrees Fahrenheit, I exactly reverse that formula. So my Fahrenheit temperature is found by taking the Celsius temperature times 9/5. That's the ratio flipped over, and then adding 32 from it. Notice over here we did the subtracting 32 first, then multiplied. Here we're going to multiply first and then add the 32. So let's say that we're listening to the radio and we hear that it's going to be 20 degrees Celsius outside today. Well, is that a nice day? Well, let's put it into our formula and see what we get for our Fahrenheit temperature. So we're going to put in 20 for C here. We do the 9/5 times 20. So again, I do 9 divided by 5 times 20, which is going to give us 36. Then we add the 32 to get that would be a 68-degree day, 68 degrees Fahrenheit. That'd be about a perfect day for me. So the last part of the basic material that I want to get through is Roman numerals. This is something I found that I was forced to learn this in like 2nd, 3rd, and 4th grade. It's not as common anymore. The basic Roman numerals are the abbreviation I is 1, V is 5, X is 10, L is 50, and C is 100. Now, in medical calculations, I've never seen anything used above L for 50, but we'll go up to 100 just to be safe. And then one that most of us were not taught when we did the basic Roman numerals was SS is 1/2. And different from our standard system, where it's just a place value, the Roman numeral system is an additive system, but there is a relative place value. So if I have something like X, V, I, what that is saying is we take the value of those symbols and we just add it together. X is 10, plus V is 5, plus I is 1, plus another 1. That adds up to 17. If I give you the symbols X, why is that not changing color for me? X, I, V, that looks similar, but the big difference is here, all of our symbols went from largest value to smallest value. When they go opposite, when there is a smaller valued symbol in front of a larger valued symbol, here I is a 1 and the V is a 5. So we got a smaller symbol in front of a larger symbol. That is subtracting. So the X is still a 10 because it's a smaller symbol after it. The I is followed by a larger symbol, so we are subtracting 1. Those symbols actually serve as a single unit. So to the 10, we are adding 5 minus 1. So that ends up being a 14. And so that's the only time in Roman numerals where two symbols combine to make a single number is when there is a symbol for a smaller value in front of a larger value. If I have IX, again, because I stands for 1 and X stands for 10, the smaller valued symbol is in front of the larger one. That means 10 minus 1, or 9. More commonly, we see smaller values like IIISS. Well, again, I is 1 in each of those cases, and SS is 1/2, so we never have a smaller symbol in front of a larger symbol. So this is just adding up. 1 plus 1 plus 1 plus 1/2, or 3.5. Or IVSS. Here I do have I is 1 and V is 5. So those are going to work together. That's 5 minus the 1, plus SS again is 1/2, giving us 4 and 1/2. So we might be asked to convert GRIV. When we deal with grains, a lot of times we put the grain, the abbreviation for grains, in front of the number, and we use the Roman numeral. So GRIV means 4 grains. And if I ask you to convert that into milligrams, we put 4 grains over 1. We're going to put grains on bottom, milligrams on top. And we know that 1 grain is 60 milligrams. So the grains cancel out. 4 times 60 milligrams is 240 milligrams. 1 times 1 is 1. So that GRIV is 240 milligrams. Okay, so enough of the basic material. Let's start looking at our dosage calculations. There are 3 methods of dosage calculations. All of them use the same abbreviations. So D, sometimes O is used, is the doctor's order. Sometimes they just use O for order. V is vehicle. The vehicle is what carries the medication into the patient. H is the on-hand dose. This is very closely related to the vehicle. Actually, the vehicle and the on-hand dose are generally tied up in the same thing. The vehicle is what carries the on-hand dose into the patient. And then A is for what is administered. And depending on the textbook or the teacher, there might be different letters used for each of these. These are just the ones that are used in the books that I use. So the first method we're going to go over is the formula. Now I'm going to be very upfront with you. I'm going to go through these methods in opposite order of the way I would consider them important. I think the formula is probably the least useful way because it requires you to memorize the formula and use it. But if it's the way that connects with your brain, that's great. I hate memorizing formulas, so I use other methods. The dosage calculation formula is the administered dose is equal to the doctor's orders divided by the on-hand dose times the vehicle. So let's look at how this would work. Let's look at an example where we have an order for 750 milligrams of ibuprofen. And our supply, we have 300 milligram scored tablets. Now again, in the stuff I've always done, a scored tablet, we are capable of going to half a tablet. A capsule, we cannot divide. It's a whole capsule or nothing. But when it's a tablet, we can round to the nearest half a tablet. So in this case, our doctor's order is the 750 milligram. The on-hand dose has to have the same units as the doctor's order, so it has to be milligrams. So the on-hand dose is the 300 milligrams in the tablet. We said the vehicle is what carries the on-hand dose into the patient. So here that vehicle is 1 tablet. 1 tablet contains 300 milligrams. So I had mentioned earlier that the vehicle and the on-hand dose are tied together. The on-hand dose is what is contained in a single unit of the vehicle or in a standard unit of the vehicle. So then we can go ahead and calculate this out. 750 milligrams divided by 300 milligrams. Well, the milligrams divide out there. 750. My calculator will clear here. Divided by 300 gives us 2.5. So it's 2.5 times 1 tablet. So the administered dose, if we multiply that out, is simply 2.5 tablets. So we would administer 2.5 tablets to the patient. I might have an order for 80 milligrams of an elixir. And my supply might stay on the label. It would tell me that it is constituted at 16 milligrams in 5 milliliters of solution. So here again, the doctor's order is the 80 milligrams. My on-hand dose has to have the same units, has to be milligrams. That's my 16 milligrams. Times my vehicle. Well, that 16 milligrams is contained in 5 milliliters. So that'd be my vehicle. So once again here, the units for the doctor's order and the on-hand dose will cancel out. We have 80 divided by 16 is going to give us 5 times our vehicle of 5 milliliters. Well, 5 times 5 milliliters gives us 25 milliliters administered to that patient. So that's the dosage calculation used in the two most basic calculations, either with tablets or a solution. Let's move on to the next method of dosage calculation, and that is the proportion. So the setup for the proportion is the on-hand dose over the vehicle is equivalent to the doctor's orders over the administered dose. So this is the value we're looking for right here, is that administered dose. Let's do the same two examples using this method. So our order, let's see, 750 milligrams of ibuprofen. Our supply is still the 300 milligram. I'm going to leave out the word scored. We're just going to assume that it says tablets. We can split them. And so what's going to go in for the on-hand dose is the 300 milligrams. And that is contained in a tablet, in one tablet. That's my vehicle. On the other side here, whatever the units are here, we need the same units here for the doctor's orders. So that has to be milligrams. And whatever unit is down here, we need the same unit over here for our administered dose. So that's going to be tablets. Kind of our rules of proportions is the units have to line up. So the doctor's order is the 750 milligrams. And now we cross, multiply, and divide. Now, since the units line up, we just worry about the numbers here. 1 times 750 is 750. Then we divide that by the 300 to get 2.5. So 2.5 tablets. Let's look at a solution-based example. So we have an order for 80 milligrams of solution, or of a medication in solution. And our supply, once again, is 16 milligrams in 5 milliliters of solution. So again, in our proportion, it's the on-hand dose, the 16 milligrams, over the vehicle of 5 milliliters. So again, that means these units have to line up. We have to have milligrams on top and milliliters on bottom. The doctor's order was 80 milligrams. That has to go on top. So to find our missing number, it's 5 times 80, which will be 400, divided by 16. Once again, we get 25 milliliters. Now, the beauty about the proportion is if you mess it up, it'll still work. All you have to make sure is that the units line up. As long as you have milligrams lined up with milligrams and tablets lined up with tablets, it'll still work out. Or milligrams lined up with milligrams and milliliters lined up with milliliters. It's still going to work. Let me show you what I mean by that. So I'm going to do this second example again, but I'm going to screw up my first ratio here. I'm going to put 5 milliliters over 16 milligrams. Well, on the other side, I have to make sure I line up milliliters with milliliters and milligrams with milligrams. So my 80 milligrams of my doctor's order has to go on bottom. and I cross multiply and divide, 5 times 80 is 400. Divided by 16 is still 25. I get milliliters. So as long as I recognize that this is what I have to administer, getting the initial ratio upside down does not guarantee we're going to screw up that calculation. The weakness of both the dosage formula and the proportion is it only allows us to do one step of the calculation at once. If there are multiple steps of that calculation that we have to go through, and we would have to apply the proportion or the formula multiple times. The third method is my favorite method. It's what we just saw in that first half hour, converting our measurements. That's dimensional analysis. Dimensional analysis, one of the weaknesses and the beauty of dimensional analysis is you can perform it without knowing anything about the substances you are working with. You are literally, just like in our measurement conversions, lining up the units so that they cancel out appropriately and just knowing the equivalencies. So I'm just going to start out with an example to show you the dimensional analysis. Dimensional analysis will always start with the doctor's orders. So let's say we have an order for, once again, 750 milligrams of ibuprofen. We have a supply, once again, 300 milligram tablets. So if I'm using dimensional analysis, I start with the doctor's order, 750 milligrams. And just like I did with my measurement conversions, I turn it into a fraction. I put it over 1. Now I'm going to multiply by an equivalency. When I was doing my measurement conversions, it was the equivalent measurement. 1 teaspoon equals 5 milliliters, or 1 kilogram equals 2.2 pounds. Here, the equivalency usually comes from the supply or the label on the bottle. And here, that is 300 milligrams, 300 milligram tablets. So that equivalency is 300 milligrams equals 1 tablet. Now I need to get rid of milligrams here. I'm canceling out milligrams, so I'll put the milligrams on bottom, so the tablets have to go on top. So 300 milligrams equals 1 tablet. The milligrams cancel out. 750 times 1 tablet is 750 tablets. 1 times 300 is 300, and then we have to divide that out. 750 tablets divided by 300 is 2.5 tablets. So like I said, the beauty of dimensional analysis did not require us to know what was the on-hand dose, what was the vehicle. We just lined up the units and canceled out to get to a unit that we could administer to our patient. So back to our order of 80 milligrams of an elixir. When we have a supply where the label tells us that it is concentrated as 16 milligrams in 5 milliliters of solution. So once again, we start with the doctor's order, 80 milligrams. And in order to work with it, we turn it into a fraction by putting it over 1. In our equivalency here, again, this comes from the label. 16 milligrams in 5 milliliters is telling us that 16 milligrams is equal to 5 milliliters of solution. We're getting rid of milligrams, so we're going to put milligrams on bottom to cancel them out. So the milliliters have to go on top. So 16 milligrams equals 5 milliliters. The milligrams cancel out. On top, 80 times 5 milliliters is 400 milliliters. On bottom, 1 times 16 is 16. And we divide it out. 400 milliliters divided by 16 is 25 milliliters. So again, we did not have to know what was the vehicle, what was the on-hand dose. The unit simply stepped in and did the conversion pretty much for us. So let's look at a little bit more complex example. Let's say that we have an order for Axle 0.3 grams. And our supply is saying we have 60 capsules at 150 milligrams per capsule. So there's extra information here that we don't need. The 60 capsules really don't mean anything to us here. We're not going to use all of them. So we start out with our order of 0.3 grams. In order to work with that, we'll put it over 1. Now we need to get rid of grams, so I'm going to put grams on bottom. However, when we look at our equivalency here from our label on our supply, that's saying 150 milligrams is equal to 1 capsule. That's not relating anything to grams, but we know our standard conversions that 1 gram is equal to 1,000 milligrams. So we can do that part of the conversion ourselves. So the grams will cancel out. Next, now we have milligrams that we need to get rid of. And we have linked milligrams here. 150 milligrams is equivalent to 1 capsule. And now the milligrams have canceled out. And the only unit left is the capsules, which is what we need to administer to our patient. So on top here, we have 0.3 times 1,000 is 300, times 1 capsule is 300 capsules. On bottom, 1 times 150 is 150. And we divide that out. 300 capsules divided by 150 is 2 capsules. So here's an example where we had 2 equivalencies needed here in our dimensional analysis to get to that result. We could have used the dosage formula or the proportion, but we either would have had to have done a conversion before we started to convert everything into milligrams, or we would have had to have used those formulas twice to get to the result. I want to make sure we get time to get to the IV flow rate, so let's do one more example here before we flip over to IVs. I'm going to do an order of codeine GRSS, and our supply is a bottle containing 15 milligram tablets. So we start out with the doctor's order again, GRSS. Well, SS means 1/2. That is 1/2 of a grain. We'll put it over 1 to make it a fraction. Now again, our equivalency here is 15 milligram tablets. That means 15 milligrams is equivalent to or equal to 1 tablet. Well, there's no grains anywhere in that, but we know from a standard conversion that 1 grain equals 60 milligrams. So we use that conversion to get rid of the grains. Put grains on bottom. 1 grain equals 60 milligrams. And the grains will cancel out. Now we can use our equivalency from the supply. Milligrams on bottom, 15 milligrams, and tablets on top, 1 tablet. And so the milligrams will cancel out, and now we can calculate. 1/2 times 60 is 30, times 1 tablet is 30 tablets. On bottom, 1 times 1 times 15 is 15. 30 tablets divided by 15 is 2 tablets. So again, like I said, the beauty of dimensional analysis, we didn't have to define what was the on-hand dose, what was the vehicle, and if we needed to do any measurement conversions, we can do that right in line with the formula instead of having to do that separately. So next, let's look at IV flow rates. So IV flow rates, there are a few different ways that flow rates can be expressed. Actually, 4 of them that I'll go over. We could have milligrams per hour, which is typically what the doctor's order is going to say. So you might have a doctor's order for 800 milligrams over 2 hours. Well, what that comes out to be is simply 800 milligrams over 2 hours as a rate. And we can reduce this rate. To reduce any rate, we take the numerical portion of the bottom number and we divide by that number. So we divide by 2 like we're reducing a fraction. So 800 milligrams divided by 2 is 400 milligrams. 2 hours divided by 2 is 1 hour. And once that bottom number is a single unit, in this case 1 hour, we can then just write it as a unit rate. So here that unit rate would be the 400 milligrams per hour. We can drop the 1 in that bottom number. That's not a very useful way of writing it out. A more useful way is milligrams per minute. So if we have an order for 480 milligrams, to be administered and infused over 4 hours. But we need this in milligrams per minute. Our dimensional analysis is going to come into play here. We have the 480 milligrams over 4 hours. We want to convert it from hours to minutes. Now, this is the first example we see where the unit we're getting rid of starts out on bottom. So to get rid of hours, since it's on bottom, we're going to put hours on top. 1 hour is 60 minutes. So now the hours cancel out. On top, we have 480 milligrams times 1 is 480 milligrams. On bottom, we have 4 times 60 minutes. That's 240 minutes. And we simply need to reduce that. So we're going to divide by the 240, the number on the bottom unit. So 480 milligrams divided by 240 is 2 milligrams. 240 minutes divided by 240 is 1 minute, so that's just minutes. 2 milligrams per minute is that flow rate. Most of the time, what we're setting up to infuse into the patient is going to be a solution. Not most of the time, all the time it'll be a solution. So it's way easier to measure it in milliliters than it is in milligrams. So we might have a flow rate that is milliliters per hour. This is going to require a little bit more calculation. We might have, now let's start out with a simple example. 1,200 milliliters to be infused over 8 hours. Well, that would be just 1,200 milliliters over 8 hours. And we divide out the 8. 1,200 divided by 8 is 150 milliliters. 8 divided by 8 is 1 hour, so that's just 150 milliliters per hour. A little bit more complex might be something like let's go 800 milliliters to be infused over 40 minutes. So to put that in milliliters per hour, we start out with 800 milliliters over 40 minutes. Now we don't want the minutes. We want to get rid of those. We want hours. So in order to get rid of the minutes, since it's on bottom, once again, I'll put minutes on top to cancel them. I'll put hours on bottom. And we know that 1 hour equals 60 minutes. So I didn't mention it before, but of course that equivalency is just one we know. It's not one we get from the problem. So the minutes cancel out for us. On top, 800 milliliters times 60 is, 48,000 milliliters. Over 40 times 1 hour is 40 hours. Then we divide out the 40. I believe that's 1,200, but it's 1,200 milliliters per hour. More common, though, for our infusions, it's milliliters per minute that we need it set up as. So if we had something like 2,400 milliliters to be infused over 4 hours, to express that as milliliters per minute, Remember, 2,400 milliliters over 4 hours. And of course, we want to get rid of the hours. We want minutes in there. So hours are on bottom. We'll put them on top. 1 hour is 60 minutes. So the hours cancel out. 2,400 milliliters times 1 is just 2,400 milliliters. On bottom, 4 times 60 minutes is 240 minutes. We divide out the 240. So 2,400 divided by 240 is 10 milliliters. 240 minutes divided by 240 is 1 minute. So that's 240 or 10 milliliters per minute. So then, of course, the final option for flow rate is drops per minute. Abbreviation for drops is GTT. That's one at the end here, Karen. If you have time, I'll have you explain to me where the GTT comes from, because I've never found a good explanation for why they use GTT for drops. But
I just know that's the explanation.
What it is. Okay, well, at least I'm not missing something obvious. That's reassuring. So in order for drops per minute, we have to know a drop factor. And a drop factor depends on properties of the fluid, properties of the infuser. It is the number of drops that equals 1 milliliter of fluid. So to use drop factor, we're actually going to go ahead and use a full formula here. Let's do an order of 1,600 milligrams over 4 hours. Our supply is constituted at 8 milligrams in 5 milliliters of solution. And we have a drop factor of 10 drops per milliliter. So I'm going to express this in drops per minute. So we start out with the doctor's order, 16 milligrams over 4 hours. 1,600 milligrams over 4 hours. Now, both of these units have to change. At some point, we need to get rid of milligrams and get it to drops. And we also need to get rid of hours and get it to minutes. Well, let's get rid of the hours first, since we have a pretty simple conversion there. Hours are on bottom, so we're going to put it on top to cancel it out. 1 hour is 60 minutes. So the hours have now canceled out. They're gone. Minutes is the unit that we want on bottom, so we're done converting the bottom unit. Now we look at the top unit. We have milligrams right now. We need to get rid of those. So I'm going to put milligrams on bottom. And we have this equivalency off the supply of our label. 8 milligrams is equal to 5 milliliters. So the milligrams have canceled out. And what we have right now is now milliliters per minute. We have one with the per minute we want, but we want drops per minute. So we need to get rid of the milliliters yet. So I'm going to put milliliters on bottom here. And the drop factor relates milliliters to drops. That drop factor of 10 drops per milliliter is an equivalency saying that 10 drops equals 1 milliliter. So we have 1 milliliter equals 10 drops. So the milliliters cancel out, and now there's a little bit of calculating to do here. So on top there, we have 1,600 times 1 times 5 times 10 gives us 80,000 drops. On bottom, 4 times 60 times 8 times 1 gives us 1,920. The only unit down there is minutes. And we have to divide that out. So 80,000 divided by 1920 is 41.66. 0.67 we'll round that to. So 41.67 drops per minute. For my examples here, I'm going to round to 2 decimal places. I understand that it all depends on what equipment you're working with, what you round to. But I'm going to go to 2 decimal places, and you guys can round differently when the situation calls for it. So I got time for a few more examples here. So let's pull out some fun ones here. So let's say we have an order for 3,000 milligrams to be administered, to be infused over 12 hours. And we have a supply. The label says that it is constituted at 50 milligrams in 8 milliliters of solution. And we're working with a drop factor of, where'd it go? 15 drops per milliliter. So I start out with the doctor's orders. 3,000 milligrams over 12 hours. We want our result to be drops per minute again. So both units have to change. The milligrams have to change. The hours have to change. Let's get rid of the hours first. Hours are on bottom. We put them on top to cancel them out. 1 hour is 60 minutes. So the hours are now gone. To get rid of the milligrams are on top. So we're going to put them on bottom here. And again, our label on our supply has 50 milligrams is equivalent to 8 milliliters. So the milligrams have canceled out. So right now, again, we have milliliters per minute. We want to get that to drops per minute. What equates milliliters and drops is the drop factor. So we'll put milliliters on bottom. And remember, that means 1 milliliter is equivalent to 15 drops. So the milliliters cancel out, and we now have drops per minute. So on top, we have 3,000 times 1 times 8 times 15 drops is going to give us 360,000 drops over, we have 12 times 60 times 50 is 36,000 minutes. And then we just divide that out to get drops per minute. 360,000 divided by 36,000 is just 10. So that is 10 drops per minute that would set that at. Let's look at one more example of IV, and then I'm going to take a step back to a regular dosage for a second. So our order is to infuse 600 milligrams over, sorry, my handwriting is horrible today for some reason, over 4 hours, or 45 minutes, I should say. We look at our supply. The label says that it is constituted at 15 milligrams in 8 milliliters of solution with a drop factor of 18 drops per milliliter. So once again, we'll start with the doctor's order. 600 milligrams over 45 minutes. And of course, we want to end up with drops per minute. Well, here we want to end up as per minute, and we're already in per minute here. So we don't need to change the minutes. So the bottom unit can stay just as it is. So we need to change the milligrams. So they're on top. We'll put milligrams on bottom. Again, we have our equivalency from our supply of 15 milligrams is equivalent to 8 milliliters. The milligrams have canceled out. And then, of course, to get from milliliters to drops, we use the drop factor again. This is saying 1 milliliter, that'll go on bottom, so we cancel out the milliliters, is equivalent to 18 drops. And so the milliliters cancel out. So on top, we have 600 times 8 times 18 is 86,400 drops over 45 minutes times 15 is 675 minutes. And we just have to divide that out. 86,400 divided by 675 is 128 drops per minute. That one's flying along a bit. Now, as you're doing these calculations, I didn't do any cross-canceling or canceling out of zeros, but some of them you may want to do that. Something like this one up here, you might have been just say, oh, let's cancel out 2 zeros there and 2 zeros there so that we have smaller numbers when we calculate. That's just fine if you're okay with doing that. I show multiplying them all the way out just because it does produce a few less mistakes. Now, the one example I want to go back to here, because remember I said that the beauty of dimensional analysis is we don't even have to understand what we're really working with. So I'm going to go back to this example where our doctor's order is for potassium chloride, 40 MEQ. MEQ stands for milliequivalents. How big's a milliequivalent? I don't know, but it doesn't matter because with dimensional analysis, we can work it out without having to know exactly what that unit is. Our supply, we have a vial that is 15 milliliters. Of a suspension, and it is constituted at 12 milliequivalents per 5 milliliters. So again, we don't know what a milliequivalent is. It doesn't matter. We start with the doctor's orders of 40 milliequivalents. We'll put it over 1 so that we can do our dimensional analysis. With the IV flow rates, the time gave us the denominator automatically. If we don't have that, we can just put 1 in there to make it a fraction. And then in our conversion factor here, we have this equivalency. This is saying 12 milliequivalents is equal to 5 milliliters. So I put my milliequivalents on bottom. 12 milliequivalents equals 5 milliliters. So the milliequivalents cancel out. On top, I have 40 times 5 milliliters, which is 200 milliliters. On bottom, I have 1 times 12 is 12. And then it's just 200 divided by 12. Giving us 16.67 milliliters. Now, Karen will probably explain to you better what milliequivalents are. I used them in this example simply because I don't know what they are, but I was still able to get an accurate dosage calculated because dimensional analysis just allows me to go through using those equivalencies from our supply labels to get those calculations complete. So I wanted to make sure I left a little time for questions. You guys have any questions?
No.
Practice.
I know that's a lot of information in an hour and 20 minutes, but hopefully I didn't overload you too much. Okay.
No.
This video, I will get this video saved and I'll process it, and sometime early next week I'll send it to Karen so she can distribute it to you guys.
Awesome.
Great.
You bet. You guys have a
Thank
great
you.
day.